Next, ladies and gentlemen, we're going to have the second keynote session. Professor Shogo Shimazu from Chiba University, Japan, will deliver a presentation on interlayer catalyst. And we're going to have Mr. Husni Wijaya, PhD, as the moderator. Well, Mr. Husni Wijaya, over to you.
Thank you very much, Ms. Rahmati. Good morning, ladies and gentlemen. It's a pleasure for me to introduce our honorable guest speaker, Professor Shogo Shimazu. Ohayo gozaimasu, Sensei.
Can you hear me?
Okay. Maybe.
Okay.
Maybe this is the second time for Professor Shogo Shimazu to give lecture in Universitas Negeri Malang. The first one on the 2018, and now the second in the I-CoRE. He is going to talk us about the catalyst of bilateral and alloy nickel metal concept and applications. This is an interesting topic that relating the importance field in chemistry, chemistry engineering, value-added biomass conversion subject, in which we are all deeply interested, and also about the bilateral what is joint publication between Japan, especially Chiba University, and Indonesian students. Before we proceed with the presentation from Professor Shogo Shimazu, let us watch his curriculum vitae. Okay, thank you. Are you ready for Shimazu-sensei? The allocation for Shimazu-sensei is 30 minutes for presentation, and then continue with 10 minutes for Q&A session. And during his presentation, if you are having a question for participants or keynote speaker and others, please feel free to write your question in the chat box. Ladies and gentlemen, please join me in welcoming Professor Shogo Shimazu.
To Japan. For the next 40 minutes, I'll talk about mainly the chemistry, the catalysis of bilateral and alloy and nickel-based catalyst, the concept and applications. Before I talk about my topic, first I'll show you a map of Japan, and here is a Chiba prefecture. The west of Chiba, there is Tokyo and downtown, and also we have Haneda Airport and also Narita Airport. But actually, the Narita Airport is located in Chiba prefecture. So the hot place of Tokyo is 634-meter high of sky tree. This is a very highest tower in Tokyo, in Japan. You can see the Mount Fuji and a very nice view, and also the Tokyo downtown around here. But the Musashi is very easy to memorize for Japanese people. because the 634 means Musashi. Musashi is in Japanese. Musashi is an old area of Tokyo. So the Musashi just memorize easy to memorize the 634 meter. And also from the Tokyo, east side of Tokyo, there is a Chiba Prefecture. You can see the long beach around here. And also we have 4 campuses, Chiba University. One is Kashiwa and Matsudo in Okana. And the main campus is around the Nishichiba campus. So coming back to the catalysis for the chemicals conversion from biomass. Hello. I will come back to the background and the concept and why do I use nickel-based why do I use alloy nickel-based metal? Okay, and usually we use unsaturated carbonates, hydrogenation by catalysts to get to synthesize unsaturated alcohols like this. And so only a hydrogenated carbonyl group around here, and then we can get the alcohol, unsaturated alcohol. Usually we use the metal, precious metal, like platinum, palladium, ruthenium, and rhodium, and also the cobalt, alumina, and zirconia from the Japanese group, but those are very not active. So we choose nickel metal because the very nickel metal is very economical, and activation of hydrogen. Second is activation of hydrogen molecules, and third is high hydrogenation of activity. But the problem is poor chemoselectivity, almost 50%, almost we can get the 100% of such not unsaturated, saturated alcohols. So we can add the second proportion, second metals, and then we enhance the parapolar group affinity, like CO, CN, and NO, and by hard soft acid base interaction to the enhancement of the chemoselectivity in hydrogenation. Okay, this is a Paulson's hard soft acid base theory. Okay, this is a kind one of the example of the fulcrum. This compound has pi interaction and also sigma interaction, but each interactions are different methods, catalysts. So we add the so we emphasize a carbonyl group by a sigma interaction. So we add the hard acid as the second metal. like tin or iron. So we we prepare the nickel tin alloy by using nickel chloride and the tin chloride by hydrothermal pretreatment. And also we get the aluminum hydroxide and nickel supported on aluminum hydroxide and also tin chloride. After hydrothermal treatment, we get nickel tin alloy supported one catalyst. So immediately, so we can get the nickel 3 tin or nickel 3 tin 2, nickel 3 tin, nickel 3 tin 4 at relatively low temperature by hydrothermal treatment. So we can obtain this alloy metal by at relatively low temperature at let's say 200 or 300 temperature. So we can use this nickel tin alloy catalyst for the application to the catalysis for the chemical conversion from biomass. So we prepared this kind of this black powder. This is a catalyst composed of nickel and tin chloride. After the dried sample, we can get we could get the XLD broad pattern of XLD. So after heat treatment, it's the treatment 633 Kelvin, we can get the very sharp peak. But it's become a large crystal size. And also we can get the supported one, but okay, so just come back backward. Okay, this is the original titanium oxide, but after addition of nickel tin catalyst, you can see a very small dot around here and over the titanium oxide. The next one, please. So the titanium oxide and silica. Okay, this is the XLD pattern of the supported nickel tin catalyst after heat treatment. Hydrogen treatment at 763 Kelvin. So you can see the broad peak around those two, titanium oxide supported and the silica supported one, but on the other hand, there's active carbon and commercially hydroxide alumina and alumina showed a very sharp peak. So you can see from those broad and sharp, you can see you can calculate the precise size. So the broad peak show the very small diameter. But on the other hand, the sharp peak indicate the relatively larger diameters. So this small size or crystal size shows very high activity. Next, please. So this is a bulk. This is a bulk catalyst. In the case of 800, in the case of, so I changed the ratio, nickel-tin ratio, 3 to 1, 3 to 2, 3 to 4. So we get a nice high conversion and high selectivity at 3 to 1 and 3 to 2. But in the case of 3 to nickel 4, we should a relatively low, poor selectivity. Okay, again, this is effective, the supportive catalyst. So alumina and commercially hydroxide alumina and active carbon, silica and nickel and zinc oxide. But in the case of titanium, we can get a very high activity and high conversion. Only the alcohol, alcohol. So we apply to the other substrate compared with bulk, and this is a supported one. Supported catalyst, titanium on the support titanium. So the titanium shows a very high activity and very high conversion selectivity. We tried the cycle experiment. And 1, 2, 3, 4, 5 until 5, we can gradually the conversion activity decreased, but the high selectivity are maintained. But after 6 times, we did the hydrogen treatment at 673 Kelvin. We get a very high selectivity, activity again. And this is a principal mechanism for the hydrogenation of propyl alcohol and propyl aldehyde, propyl and propyl alcohol on the nickel-tin alloy catalyst. So mainly this sigma interaction occurs from the tin to the oxygen lone pair. This is a sigma interaction. Almost 100% of alcohol, propyl alcohol. Okay, this is another second method, ion catalyst. Ion alloy catalyst we prepared. Okay, this is just introduction. So So we prepared the nickel 3 iron 1 catalyst. This is alloy. Only we can see, even we change the ratio nickel 3 nickel to iron, we got only one type of catalyst. We only one type of catalyst. Nickel 1, nickel 3, iron 1. So relatively high yield and selectivity. But the problem is by using a different substrate, we carry out the different substrate. We carry out the hydrogenation by using nickel iron alloy catalyst. In the case of aromatic carbonyl groups, we can get a very high selectivity and high conversion and high selectivity. But on the other hand, in the case of conjugated one, we get a low selectivity. We also apply to the other substrate. With this, we get sometimes unconjugated one, we got a high selectivity, but next one, please. Recyclability of nickel iron alloy catalyst by using only we can get a hydroxyl alcohol by the chemical hydrogenation. But in that case, but other saturated one, we can, okay, I'll show you later. Next one, please. The high selectivity. But in the case, so we sought the mechanism for the unconjugated carbonyl group. And again, the oxygen lone pair and nickel sigma interaction occurs, then we can get the high selectivity. But in the case of conjugated carbonyl compounds case, we get the sigma interaction between CO lone pair and tin, but isolation occurs like this. So conjugated one doesn't work, and aromatic or unconjugated one show the high activity and high selectivity by using nickel iron alloy catalyst. Another topic is nickel tin alloy catalyst for the gamma bioreactant from organic acid. Okay, this is a very short description from the uranic acid. We hydrogenated, and then we can get the gamma bioreactant, almost 99% yield at in water for 3 hours at 393 Kelvin. Another one is nickel. Okay, nickel yttrium catalyst for the peripheral hydrogenation and hydrogenolysis to the 1,5 pentadiol. Okay, one of the moderator Husni did this work. The nickel yttrium catalyst can show the 1,2 or 1,5 pentadiols after the hydrogenation and hydrogenolysis. And Husni clarified this mechanism. First, the peripheral hydrogenation occurs, and then we can get the peripheral alcohol. But the peripheral alcohol has two cleavage by the hydrogenolysis occurs. This point, we want 2 pentadiols. But in the case, so this one is 1,5 pentadiol. So we cannot reduce the 1,2 pentadiol from the peripheral alcohol. But after the hydrogenation, we can get tetrahydrofuryl alcohol. Only we can get the 1,5 pentadiols, as shown here. So Husni add the ruthenium, and he also accelerates this reaction hydrogenolysis by THFA from THFA tetrahydrofuryl alcohol to get the 1,5, only 1,5 pentadiols.
I'm sorry, Sensei. Only
Okay.
3 minutes more.
3 minutes only? Okay.
Yes.
Nitro group. Okay, hydrogenation of nitro group to get the secondary amino amines, amines. But so far we use the precious metals. Okay. And by using the nicotine alloy catalyst, we can get only rehydrogenate natrium group to the amino group. Conversion 100% and sensitivity 87%. So this is a physical mixing. This is PM means physical mixing. So in that case, we just mixing by physical mixing nickel and tin. We cannot get amino styrene. Okay, and also the nickel metal show the very high, not selectivity. But after we use a nicotine alloy catalyst, and we get very high activity of amines. Amino styrenes. So increase the pressure, we get a very high activity, and also we use other substrates, and we get very nicely good selectivity and conversion. Okay, next please. So we so this is the interaction between the catalyst and oxygen sigma interaction is important in this case. This is a mechanism. Next, please. Okay, the final. This is the final slide. This is the catalysis for chemical conversion from biomass by using a one-pot reaction. So one-pot reaction is nitro group, nitrobenzene, and also the benzaldehyde. So after we got aniline, only we got a benzaldehyde. The reaction is benzaldehyde. We get a very high selectivity. But in the case of solvent, it's depends on solvent. Like alcohol or amide group, the low selectivity. But in the case of xylene and methylene, we can get 100 almost very high activity, selectivity. Okay, next please. So the aniline. Okay, this is a benzyl aniline, and this is a phenyl aniline. Both are condensation product from the aniline and benzaldehyde. But after, okay, benzyl alcohol are produced a little bit. But addition of molecular shapes, we can accelerate the reaction speed, but still we can get the benzyl alcohol. Next, please. So we use a recycled test. After current, 75%, but the selectivity is very high, maintained. Next, please. So this is a fresh catalyst and spent catalyst, almost the same. So even after the several times used.
Ayo, mana ya Papa ya? Kalau enggak kata Papa.
Okay.
Ayo ya,
This
mana
is
ya
just
Papa ya?
one.
Mana
Okay,
Papa
this
ya?
is
Mana Papa?
acknowledgement. Just one. This is my. Here is my page. This is a picture of the mostly the integration students, PhD student who's in here, and Wahyu is now working in Japan. Topic, and also the Sato, Leo Satora, and Ludian Sono. Thank you very much for your attention.
Okay. Thank you very much, Professor Shogo Shimazu, for the valuable knowledge. Then, is there any questions? From other keynote speakers, invited speaker, and also participant, please, if you have any question for from Professor Shogo Shimazu. Okay. Maybe one question from me, Sensei. Okay. your research regarding it means that the addition of the second metals tin and iron or yttrium have enhanced the chemosensivity of what is in the unsaturated alcohol, especially carbonyl or nitro groups. Okay. How about it is the reaction mechanism for gamma ferrolactone? Is this similar with the hydrolysis of furfural to 1,5-pentadienyls?
Okay. You mean that the hydrolysis
Yes.
of the furfural?
Yes, furfural to gamma ferrolactone.
In the case of furfural, the first furfural hydrogenated occurs, and after the unsaturated CC double bond, the furfuryl alcohol. Once we get a furfuryl alcohol gives 1,2 pentadiols, and also mainly the 1,5 pentadiols. But small amount of 1,2 pentadiols was produced. So that is one of the big problems. So after you add the ruthenium accelerate the hydrogenation speed after until tetrahydrofuryl alcohol. So this is important of the important point. The furfuryl alcohol is so in order to get if you get only tetrahydrofuryl alcohol, you can get only 1,5 pentadiol. But even if you get the furfuryl alcohol, instead of tetrahydrofuryl alcohol, if you furfuryl alcohol, in that case, if you get 1,2 pentadiol, so very difficult. So you can accelerate until the tetrahydrofuryl alcohol. Now we can find a good catalyst for the tetrahydrofuryl alcohol. But ruthenium is not working. Still working in the still working on that.
Okay. Thank you very much, Sensei. I think there is so thank you very much for valuable knowledge and that you share and fruitful discussion in this section. Now it's time for giving certificate as a keynote speaker I-CoRE 2021. Please. Let's have a photo session, Sensei. With me, I think. Please stay cheese and smile. Okay. Thank you very much. Have a nice day. Professor, stay safe and health, and see you in other occasion. Thank you very much. Now I get it back to Ms. Rahmati. Thank you very much.
Thank you so much, Professor Shogo Shimazu, for the very systematic and elaborative presentation. And thank you, Mr. Husni Wijaya, for leading and guiding the discussion.